Hi everyone, this lesson is 411 on linear programming for Algebra 2 Honors. Is Chapter 4, Day 9. Let's get started. We're going to start off with the Piecewise challenge, and instead of me giving you the equations, what I'd like to see from you is that you give me the equation. So there's 3 different equations, and it looks like there's some continuous lines here, and then open circle here and here, line. Okay, so what's happening here is that what we have is we have 3 different lines. So this one right here is going to be going on forever, and it looks like my y-intercept is -2, and then my slope is 1. So for that equation, generally a y equals mx plus b equation. My y-intercept is -2, so that'll be -2. And then my slope is 1, so that would just be 1 times x, which is x, and then equals y. So as I'm putting this into f of x notation, I would say then that this would be like this, right? Because you have 3 graphs. We are going to say the first graph is x minus 2 with a restriction that x has to be, let's see, we're going to say that this line actually covers that. So we're going to say that x is less than or equal to 6. Then, and that covers this straight line. This is a parabola. And for my parabola, it does look like I have points 1. Let's say that this was at 0, then this would be 1, 1, and that would be -1, 1. And what would be 2? 2, 1, 2, 3, 4. Okay, so that means that this graph right here is actually a y-squared graph, y equals x squared. So y equals x squared. The only difference is that it actually has a point at 8, 0, which means that the graph has been shifted to the right 8 units. So it's not moved up or down, it's just shifted. So our equation for this would be x minus 8 quantity squared. Now, if I was going to move a graph up or down, right, just lift this parabola like this, if I were to lift that, and go up 5 units, then I would add the 5 right here. But it's not, so I just leave it like that. And so we just have that equals x squared. And so this is going to be quantity x minus 8 quantity squared. And we're going to say for this one that because you can't have necessarily 2 points at the same place, but they are kind of at the same place, I'm just going to make this one open circle at the end for both. So this tells me that x has to be more than 6. So we're going to go x has to be greater than 6, but less than 11. And then lastly, we have this line right here, which I do have my y-intercept, and that's going to be 20, 0, or sorry, not my y-intercept, but just a point at 20, 0. And it also says, it does look like my slope is going up over, so that actually is going to be a negative. That, because I mean technically it's going down, even though I'm going up and over, it's still 1 and 1. So with that, slope equals 1. So I'm going to plug this in. So y equals mx plus b. I know my slope is 1, so that's going to be x or plus b. But what also, I don't have my b value. Like I don't know where it's crossing the y-axis, say somewhere up here. I don't know what that value is. So I'm just going to use my point and plug that in because I do know the slope is 1. So but the only variable I don't know is the m. So we're going to go 0 is equal to my slope, which is 1, times x, which is 20. Although I have to say this. So even though my slope is 1, 1, that would be positive. This slope actually being negative. Slope is -1. All right, so 0 equals -20 plus b. So I'm going to add 20. So it does look like b is equal to 20. And so therefore, my equation is going to be y equals mx plus b. So it'll be negative, m is -1. So negative x plus b, which is 20. So this will be negative x plus 20. And then the only other thing here that you would say is that it does, it's not technically going all the way up, right? Because it stops right here. So we just had to use that to figure out what the equation was. But it has to be greater than or equal to 11. So we're going to say x is greater than or equal to 11. And for here, I knew there was an arrow like that. And so that's just going to keep going. So these are my equations, these three. And then these are my restrictions. X has to be greater than or equal to 11. Okay, so this would be the piecewise challenge. Check, we did it. All right, so the next thing basically is just what are we doing? We're talking about our learning targets are basically using information about two independent variables, finding the pair of values that maximizes or minimizes a third value. So basically, you're going to get some sort of real world problem. And you are going to have a lot of constraints. And those constraints or restrictions translate into inequalities. That's what those are. And, you know, these are going to be kind of fun for sure. And I mean, like, you never know what's going to happen and what's going to show up in your, you know, in your graph. And I mean, maybe I can get this to work. I'm not sure. Well, I think I might be able to. We'll see. Let's see. Possibly. So yeah, as I was going through this and hiding some little fun stuff in the graphs, I always like to do that. Anyway, okay. So let's get to the first kind of problem that we're going to see. And that's just, what is it? What are we looking at? Linear programming basically is an optimization technique for a system of linear constraints, what we just said. An objective function defines the quantity to be optimized. The major goal, so your job, is to basically find the one value that maximizes or minimizes, depending on the graphs, the objective function. So you're looking at this graph right here in green. You see all of those different graphs here. There's 1, 2, 3. It looks at least 3, possibly 4, depending if the x and y axis were, you know, a restraint. And what would be the maximum value, right? What is the maximum point of efficiency, etc.? So that's what they want to know. This is actually very useful for business, and your parents probably, if they are in the business, they use stuff like this too. So you can even ask them. Warmup, write an expression meaning 3 less than x. So 3 less than x, so that's going to be something like 3 less than x. Write an inequality saying 3 is less than x. So 3 is less than x. Write an inequality saying x is at least 3. So it could be equal to 3 or more than 3. Write an inequality saying x is between 4 and 7, but they did not say it equals that. So these are just like a little bit of a warm up to something like what a constraint might look like. This is what they're talking about. So we're going to just practice one problem of graphing inequalities, and then we're going to try to find the max point from where you're at. So the first equation is that we're going to graph x is greater than 2, but less than or equal to 6. So let's see. I'm going to make this maybe a little bigger. And then, so x is greater than 2. So here's 2. And for this graph, so we have this line, and here's x equals 2, vertical line. And then you've got x equals 6. So 2, 3, 4, 5, 6. Here's 6. And so what you know is that x is greater than this value, but less than 6. So you would say anything in here so far. Then you have y is greater than -1. So here's -1. Here's my graph of y equals -1. And it's saying greater than, but not equal to. So this is an issue. See my line right there, that's not appropriate because it has to be actually a dotted line because it's not equal to. So then it's got to be greater than, so that then is everything shaded above. So that means that all the stuff I shaded below is out of luck. Okay. Then this, so we did this. This one, I don't know what it's saying. So let's solve for y. So we go negative 2y is greater than or equal to negative x minus 6. So I'm going to divide everything by negative 2, and I get y is less than or equal to 1/2 x plus 3. So this graph goes up, let's see, 0, 0, 1, 2, 3, starts here, goes up 1 over 2, up 1 over 2, up 1 over 2. And this is a solid line, so I'm going to graph this as a solid line. And this one says, did I change my, yep, I changed that. So this one actually says y is less than. So again, everything below, but you know, we've already covered that, because even though all this stuff here is below, if it's not included in the original values, then it's, you know, it doesn't exist. And then this one right here is a little bit different. This one has been put into point slope form. Given the point, which is 4, 5, we have a slope of negative 1/2. So let's plug that in. So let's go 1, 2, 3, 4, 1, 2, 3, 4, 5. This point right there. From there, we have a slope of down 1 over 2, down 1 over 2, or up 1 to the left 2. And this is also a solid line, so I'm going to graph this like that. And therefore, this is going to be less than. So everything that I shaded above now is gone, and that includes this little part in here. I don't know if I can get just that little tiny part. Okay. All right. And so now what we're looking at is the max point. Well, that's up here. It's right there. And so what that max point would be is the 1, 2, 3, 4, 1, 2, 3, 4, 5, 4, 5. And so, you know, depending on, you know, what my question was in the real world, that would just depend on, you know, what my answer was. But 4, 5 is the max point for this equation. So linear inequalities have graphs that are regions. So like this one right here is a problem that you would do. It says, given the following requirements, the sum of x and y is at most 10. Y is less than twice x. And y is at least 2 more than 1/3 of x. So what I prefer you to do right now is to actually take a moment. I want you to pause the video, and I want you to write down the requirements. You're going to check those with me, and then we're going to graph this. And so I'm going to pause, and you do the same. Our constraints, and these are our values here for our restrictions. So we're going to plot each one of these equations. So the first one, I'm just solving for y. We have y is less than or equal to negative x add 10. So that means we're going to start up here at 10. And again, definitely use Desmos to graph to see if you can, or to check at least. So let's plot up 10. So we have 10 up here, and our slope is negative 1. So that's going to just come down, and it's solid. So make sure you check for that. So there's one equation, and it says less than or equal to, so we're technically talking about all this space here. The next one says y is less than 2x. So that means that there's the y-intercept is 0. And then we go up 2 over 1, up 2 over 1, 2, 1, up 2 over 1. And this one says y is less than. So this is definitely a dotted line like that. And it says less than. So that's all this shaded area. And so far, this area in here is my double shaded area. So I'm going to get rid of all the other shaded area that I wasn't part of the first equation. And then the last one is 2 is my y-intercept. So I'm going to go up 2, put a point here, and then my slope is up 1 over 3. And this is a solid line also, so that looks like that. And then what you're doing is that says y is greater than. So that's everything above. And so therefore what you're doing is finding this max point. That's what you want to find. So we plotted the graph. This shaded region is a solution to my graph. Now, if I was asking for, I don't see them asking that, but if they were to ask for the max point, that value right there, you have to understand that if I don't see an actual point of intersection, then what I need to do is I need to take those two equations and set them equal to each other. Meaning those first two equations right here, I would set those equal to each other. I would say, where does x plus y, equal y, or what do they equal each other? So for this one, the top one, which was y is less than or equal to negative x plus 10, I would take that value and then I would set it equal to the second equation, which was equal to 2x. So if I said 2x is equal to negative x plus 10, that would be 3x equals 10. So that means x equals 10 over 3, which is probably why the value in the point right here is a little bit hard to read. So x would be 10 over 3. To find y, I would have to plug it back into one of these equations. I would just pick the 2 times x, which would be 20 over 3. And therefore, that would be my intersection point, which would be this value right here, if they asked me for the max value, but they didn't. So therefore, the actual answer is just that shaded region inside there. And a possible question that could be on a test might be, choose a solution to the equation. So not only would you have to graph this, but you would also have to pick a point that was inside of that area. And if you just didn't make your graph very accurate, you just pick a point somewhere in here, like, what is this? 1, 2, 3, 4, 1, 2, 3, 4, let's say 4 or 5. And I would need to plug it into all 3 of these equations to see if that was actually accurate, if that worked, if it satisfied all 3 of the equations. Okay, so problem number 2. This is the clothing sale problem. It says student council decides to raise money by selling imported clothes. Let X be the number of shirts imported and let Y be the number of dresses imported. The import order must meet the following requirements. So I'm giving you 4 requirements. Now, based on those 4 requirements, I want you to write the inequalities, which are those 4, restrictions, and then plot the graph of that feasible region. Okay, so again, pause your video. That's what I want you to do. Pause your video and then really try to write these restrictions down. I'm going to say what they are. The first one says the total number of shirts and dresses must be at least 10. So 10 or more. So that means 10, it could be equal to 10, but it has to be more. The number of shirts must be between 5 and 27. Now, inclusive. See, if they didn't put that word inclusive, then between means not including. It means, you're standing in between somebody, but not like touching them. But inclusive means you're standing next to them and rubbing shoulders. So the number of shirts must be between 5 and 27, including. The number of dresses must be less than twice the number of shirts, but at least 1/6 the number of shirts. So those right here, that's two little restrictions within one question. And then you've got 4 times the number of shirts plus 3 times the number of dresses. Has to be at most 135, which if it's at most 135, then that means it has to be either 135 or less. So again, pause the video, take a moment and do that. Okay, so I'm going to assume that you did. And we're going to go over the questions that in the restrictions. And the first restriction says the total number of shirts and dresses must be at least 10. So X plus Y is at least 10. I would recommend that you solve for Y for graphing purposes. So we're going to say Y is greater than or equal to negative X plus 10. So that would be my first equation to graph. The next one says the number of shirts must be between 5 and 27. So here we are. Now, just a note, when you see something like this, I understand that it's easy to, write the numbers, just make the lines, but don't forget this could also be split up into two different questions, like two different answers, right? So if we know that x is greater than or equal to 5, that's this part right here. And we also know that x is less than or equal to 27. So you have two equations there. It's up to you how you want to draw those, sketch them, however, but they are vertical lines. The number of dresses must be less than twice the number of shirts. So that's 2. But at least 1/6 the number of shirts. So like I said, this is a little bit, you had two different, restrictions. So first part says the number of dresses must be less than, this is your dresses, twice the number of shirts, but at least 1/6. So at least means that value or more, right? 1/6 x. Okay. And then 4 times the number of shirts plus 3 times the number of dresses, that's easy here, must be at most 135. And then again, I would suggest you solve for y. So 3y is less than or equal to negative 4x plus 135. Y is less than or equal to negative 4/3 x plus, let's see, 3, 8 plus 1 is 9. So 3 divides into 135 evenly. So, and you just have to add the digits up, right? 5 plus 3 is 8 plus 1 is 9. So I know, because 3 is a factor of 9, I know that 3 will divide into 135. That's kind of tricky, isn't it? Okay, anyway, 3 divides into 13 4 times, right? That's 12. 1 left over. 3 divides into 15 5 times, so put that there. So that's plus 45. So obviously, you are not going to use this graph and to, plot, because it's like, counting over, there's maybe 10 left and right. So you're just going to have to make some sort of sketch. And in doing that, so we were going to start up at 10. Let's just say, because I'm going to be going up 45. So for sure, I'm going to need to just guesstimate what these values are. Is that the highest one? Yeah, I think so. So we'll just say way up here is 45. We'll say that's 45. And we'll say, let's just say this is, if that's 40, 30, 20, we'll say this is about 10. Okay, so basically this first question says starting at 10, and the slope is -1. So we're going to say this goes down like that, and it is solid. And it says, but it's shaded above. So everything this way, right, would be a solution. This one says x is less than 27. I'm going to say here's 27, okay? And then let's just keep going with this like that. So here's 27, and then the other value would be 5. So I don't know, we'll just say this is 5 here. And so what that means is everything, so not everything now, because it's got to be in between there. So nothing on the outside and nothing going that way over here either. Okay? And then the next one said less than 2x. So 2x starts at 0, goes up to over 1. And so this one is a dotted line, and it says less than. So now we're shading below, which then means none of this works. Okay. And then greater than or equal to 1/6. So 1/6 starting at 0 again, 1/6. So that's going to be like more of a wider, and that's a solid line also. And it says greater than. So that is really a good one, because that's saying everything above that line. That knocks everything else out. So above that line, so now we're just looking at this stuff in here, not including that over to the left. And then the last one basically says start up here at 45, down 4/3. So it's going to look something like that. Shouldn't have the same slope as that. Yeah, let's see if I can fix that. Maybe, not sure. I think I'll just delete it and draw it again. And if I deleted it and drew it again, I'm going to try not to get the same kind of slope. So there we go. Let's try that. And that is going to be less than. So that's all this shaded region. So the final little region area is all this stuff in here. Okay. And in getting that value, okay, so we graphed it. Let's check our graph though, right? Let's check it. So I'm going to move this. Dun, dun. And see how we did. Pretty good. Of course, it's a little bit off because of our, it's not very much to scale. But let's see if I can fix that one there and move that off. There we go. Okay, so kind of something like that. All right, right on, good. All right, so that's what we have, is that like region inside there. All right, I like that. So now the question then, let's go back. What was the question? Plot the graph of the fee. Oh, they didn't ask anything else. Okay, all right. They just said graph, so check we graphed. Max point though, just FYI, would be this point right here, right? And so just note that that point right there, that would be my max point. If they ask me for like, what's the maximum profit or something like that, that's what I would use. Okay. Okay. So again, you've got work and you've got an assembly line producing no more than 25 breakers and 16 good buddies per day. So we've got, suppose you work for a small company that makes high quality CB radios. They wish to optimize the number of the two models that they produce. So they've got breakers and they got good buddies. So since you are now an expert at linear programming, your boss assigns you the job. So find the following information. And so these are all like their prerequisites. These are all their rules, their constraints, their restrictions. And your job is to actually put all of this together. So an assembly line can produce no more than, so that's less than 25 breakers and 16 good buddies per day. So you've got less than those values. No more than 32 radios total can be produced per day. So that means that the breakers plus the good buddies have to be less than 32 or equal to, no more than 32. So that means you can have 32, but not more. They can spend a total of no more than 189 man hours a day. It does take 7 man hours to assemble a breaker and 3 man hours to assemble a good buddy. I wonder if that means that the breakers are better because it takes longer for them to assemble. I don't know. They can spend at most 68 man hours per day. It takes 1 man hour to test a breaker and 4 man hours to test a good buddy. And the number of breakers produced per day must be more than half the number of good buddies. So once again, it's up to you to pause the video, plot, put your values in, what you're going to be using for CB radio or, for good buddies and what you're going to be using for breakers. And you need to establish your inequalities and then join back in when you're done. Okay. And so hopefully that you did that. And so we're going to define our variables. So we've got B, I'm counting as breakers, and you could have used any other, whatever you wanted with that. We have B for breakers, we have G for good buddies, and then P is the number of dollars of profit per day. So it says the assembly line can produce no more than 25 breakers. And so, you've got B is less than or equal to 25, and the good buddies is less than or equal to 16. Keeping in mind that they both have to be greater than or equal to 0. Next question says, no more than 32 radios total can be produced per day. So that means that the sum of the breakers and the good buddies has to be less than or equal to 32. However, and then they just solve for B. That's all they did right there. And then they can spend a total of no more than 189 man hours a day assembling the radios. It takes 7 man hours to assemble a breaker. That's why you're multiplying by 7. 3 man hours to assemble a good buddy. We're multiplying by 3. And solve for the breakers. and they can spend at most 68 man hours per day. So the sum of the two would have to be less than or equal to 68. But just keep in mind that 1 hour to test a breaker. So that's just 1 times B. And then 4 hours to test a good buddy. Solving for B, move the G over. And lastly, the number of breakers produced per day must be more than a half the number of good buddies. So that's greater than, must be more than a half. So not equal to, but more than. Okay, so very important distinction there. Okay, so your job would be to find the optimum point at which the maximum, and so I would at this point like assume that you would use Desmos or graph on a piece of graph paper, because your job is to find the optimum point at which the profit is at a maximum and the number of dollars they would earn per day by operating at this point. So take a moment and graph everything that you have, and then pause the video, start it back up again. And as you can see that this is the graph. It's a little bit busy with all of the different equations on here, but what the most important thing is this right here, in that we're looking for the max point, and it kind of looks like to me that max point, after it's all said and done and graphed and all of that, is right here. Okay, that's it right there. And that's where this graph here and this graph here intersect. Now, I mean, I can give like an approximate value, right, of like less than 10, and in the 20s, that looks like 25. So therefore, it'd be less than that, right? So, what you're doing is you're trying to find that point. Well, to find that point, the only way to find that point, I mean, of course, if you have Desmos, you just like push the cursor right on the point of intersection. But if I didn't have that, what I would do is I would set these equal to each other. And I would say negative G plus 32 is equal to negative 3/7 G plus 27. And I would then basically solve for G and B, your good buddies and your buddies. And when you do that, you of course get this answer that I have for you right there. But it's really, really important that you understand like how you go about getting that, because once you set these two equations, because there's a lot of different equations, right? Your job is to find, the max point, which looks like, that would be the most profitable to me. That's what that looks like. So, that's going to be the most profit for you, and where they're going to make the most money, and you're going to sell the most, of the good buddies and the breakers. So this just says the company makes you a profit of $40 on each breaker. Still, this is like the never-ending problem, and $20 on each good buddy. So your job is to write an equation expressing dollars profit earned per day in terms of the number of breakers and good buddies produced each day. So again, take a moment and think about what that's actually asking you. Pause the video and then get started back. And what you're looking at here is you're looking at, coming up with something, $40 for each breaker. So you're multiplying by 40. $20 for each good buddy, you're multiplying by 20. And so you're going to take that value of $40 for each breaker, right here. You're going to take this value for $40 per breaker and $20 for each good buddy. And that right there is your profit, okay? So right there, profit. And so what's going to be the profit? Well, you already know that this point was our max point. Well, all I have to do then to find my profit is to plug this in to good buddies and breakers, right? And then I'm done. And remember, don't get them confused, because this is good buddies and this is breakers. And then they're flipped for this right here. But so this one is going to be multiplied by the 23. And then the other one, here, I've got it right here. And then the other one will be multiplied by the 875. So that what that means is that they're bringing in some money. They're making $1,105 per day just because they're making $40 each breaker and $20 off each good buddy. So what that is, again, is basically just you, again, finding the max point and then coming in and saying, what is the profit going to be at my max point? Okay. So the only other thing I want to talk about is just if you had any project questions. I thought this was due October 2nd, possibly the 7th, I'm not sure. That might have been an error. So I'm going to just leave this off and to be determined. I think we'll go with October 7th. That seems fair. Anyway, you need a minimum of 5 steps, but not to exceed 15. You have to use at least 3 types of functions. You're going to, I was going to have you actually take a screenshot of the image, but since we now have our class on Desmos, I've created this project on Desmos, and I want you to view that, and your work is going to go into that Desmos class. And there's a spot for that. And so you're going to make your assignment within Desmos class. And then, of course, the only other part to that is the reflection. There is also a rubric attached. And so you can find the project either on Desmos, and I'll also put a copy or a link of the, requirements on your slate. So you can have that. Your homework, only 2 problems, page 163, 4, and 5. That's it. Yeah. Good luck, and please come and see me for office hours if you have any questions at all. Thanks for watching.